Hello together. We find ourselves now at the end of the section on the Hahn-Banach theorem. We have so far stated the theorem. It was actually two theorems, and then proven the theorem and then derived several corollaries. The last of which will be here, proven today early on. It's actually, I don't call it corollary, it's bigger than that. It's a theorem, but a consequence of the Hahn-Banach theorem nonetheless. And as I said, so these consequences, I said this at the end of the last video, these consequences right now, they might seem strange. It might not be clear why we care for them much, but this will be disclosed in time. So right now we just accumulate that knowledge and then apply it later on. For instance, this one, which is written here. So if you have a Banach space X, real or complex, and then if the dual space is separable, then the space itself has to be separable. Okay. Natural question is to ask whether this is a two-way route. So given a separable Banach space, is the dual space necessarily separable? And the answer will be given in the next section. So this theorem closes out the current one and builds up the next one. And the answer is in general no. This only works for a special class of Banach spaces that will be discussed very soon, probably starting in the following video. Okay, but now we prove this here. So given a separable dual space, we will conclude that the space itself is separable as long as it is complete. So proof. Well, first off, by separability, we can pick a countable dense subset, say f sub n, be a countable dense subset in X. Okay, now what we will first do, we will construct a candidate for that countable dense set in X. That is, well, if we manage that, right, then the theorem is proven. So how to do this? Well, first the general observation, then for every natural number we can choose non-zero element xn in X so that fn xn is at least 1/2 the operator norm of fn. Why is this? Well, for otherwise, so what's the contrary of this statement? Well, it would mean there exists an index n naught, so that fn of x is less than 1/2 fn for all x in X, right? That's a contrary statement, but if that were true, then if you just optimize the left-hand side over the boundary of the unit ball in X space, then you would get on the left the operator norm of Fn, so then you would have this nonsense inequality. Well, why nonsense? Because if you have two non-negative real numbers, then one cannot be strictly less than half of itself, right? So yeah, if you have, I shouldn't have said two non-negative real numbers, if you have one non-negative real number, then it cannot be strictly less than half of itself, right? So that's why you can indeed pick these elements xn in the fashion indicated up there. Okay, so now we construct our candidate for the countable dense subset in X. D. These will be simply all linear combinations of those elements xj. Okay. Now this has to be countable, so you should either choose those coefficients to be rational, or, well, being complex numbers with rational, real, and imaginary part, right? So that you have something countable. You can't choose real alpha j's or complex alpha j's, because those are not countable, right? So alpha j, let's do it like this, is in Q if the field is R of X, and it is in Q plus IQ if the field is, well, the complex number field, okay? And n, well, can range through all natural numbers. But that's not a problem because the natural numbers are countable, right? I need to worry about the alpha j's, okay? So let's look at this set here, all right? And then we will prove now. So this one is countable dense. Well, first of all, it's countable by construction. There's no question there. And so we have to prove that it's dense. So first let's write it out. Denote the set of all finite linear combinations of the xn 1 up to infinity with, well, I will say rational coefficients if the field is the complex number field. By that I mean then rational, real and imaginary part. Rational coefficients. All right, so since D is countable, that I just explained, countable, it is now sufficient to show that D is dense in X. And for that we will use the Hahn-Banach theorem, one of its corollaries, and the argument goes as follows. So if it were not, so proof by contradiction, if it were not, then there is a point y in the complement of D and a linear functional f with f of y different from 0, but f vanishes completely on D. So f of x is equal to 0 for all x in D. Why is this? So one of the corollaries to the Hahn-Banach theorem was that guy where you pick a subspace y in a bigger space X, not necessarily closed, but now you pick a point y in the complement x minus y, which has positive distance from y, okay? And then it was asserting that there exists linear functional with those and those properties. So that's precisely what we're doing here, right? So our subspace there is y, which is clearly a subspace because you're looking at spans of the xj's with rational coefficients. And then you take a point y, which is in the complement of D. And since D is not dense in X, the distance between y and D is indeed strictly positive, okay? And that's why I have here that I can find linear functional on the whole thing that is different from 0 at y, but vanishes on all points in that set D, okay? That is a consequence of one of the corollaries to Hahn-Banach. All right, so we have this. Now let fnk be a subsequence of the given countable dense subset. Or by the way, here up front, I just see I have a typo. I said let Fn be a countable dense subset in X, but of course it's in the dual space, X star, all right? Right, so now let Fnk be a subsequence which converges to F as k tends to infinity. And this subsequence surely exists because remember we select a dense subset up there, right? So now here I have this functional f in x star, and a set being dense in x star means, you know, I can get arbitrarily close to the given f, and that means I can just select the subsequence of that given subset up there that will converge to that f, and that's all that I've written there. Okay, so we have this. Then now what we will compute is the following. So the operator norm of the difference of fnk to f. Well, this is an operator norm, so this is a supremum of, well, f of x minus fnkx divided by norm of x, on top the complex modulus, and then you range x over over the whole space being non-zero? Well, because of this, it is at least as big as, well, f minus fnk evaluated at the xnk's. Okay? So remember those points, xn. Now I just select the corresponding subsequence. So we have this. But now, what I know about my functional f is that it vanishes identically on x and k. Yeah, but these guys here, it doesn't vanish on x and k, it vanishes on d. And those x and k's, they are chosen from d. So that means this part here is equal to 0 because f vanishes on d. So what I have up here is simply f n k x k. I don't touch the denominator. And then remember up front I had this inequality, how the xn's and hence its subsequence xnk is chosen. Here I forgot the subscript, xnk. Well, they are at least a half. And then since it's already divided out, the norm of fnk. All right? Yeah, but remember the left-hand side, as k goes to infinity, this goes to 0 because fnk, the fn's already as n goes to infinity, the fnk's converge to f as k goes to infinity. And this would mean in turn, which shows that fnk goes to the 0 functional as k goes to infinity. So f itself is the 0 functional because limits are unique, is the 0 functional on x. Yeah, but this contradicts that the value at y is different from 0. So our assumption was false, and that was after all that d is not dense, hence it must be dense. So d is dense and thus x separable. Okay, that's the statement. All right, so given a Banach space, if the dual space is separable, then the space itself is separable. All right, very nice. And it was proved by contradiction, and we relied on, again, functionals with certain properties, and for that you use the Hahn-Banach theorem. Okay, good. Now, the next section. So as I said, one can ask oneself whether the converse statement of the last result holds true, and I said in general that's not the case, and this will be one of the many results that we will discuss now in the next section, duals and double duals. Okay, so we begin with the following theorem. This defines a new object, so it's theorem and definition in one if you want. So if you have a bounded linear transformation, be a bounded linear transformation between two NLS, yeah, let's write the dependency on it in the norm, x and y. Then there exists a unique, well, this will be a bounded linear transformation between the corresponding dual spaces, but the order is swapped. You don't go from x star to y star, but you go the other way around. So you go from y star to x star, and that thing will be denoted in this module by a to the power t. Okay, that's a t, not a plus. And it is called the dual. That's why the headline here of this section. So this is a dual linear transformation. And what is the defining property? So that, well, ATF. So if this is really going to be a linear functional that starts with something in the dual space of y, then it must act on a linear functional. That's why AT acting on F. And then if you believe what's written there, then it should spit out a linear functional in x, and that's why I can evaluate it here on a point x, right? And how is this thing defined? Well, let's use a definition here. Maybe not a definition. I mean, I'm claiming there exists something with this property, so that property shouldn't be the definition. So it is f of a of x, and this is for all x in x, and for all linear functionals on y. Okay. A few properties. There will be more later on. The map, which assigns to a given bounded linear transformation A its dual, is a linear map, and it is an isometry. Remember, those are the norm-preserving maps. Okay, that's the statement. There is some other terminology used in the literature. If you look into other textbooks, I will call it a dual. There are other words out there. People call it, if the underlying normed linear spaces are complete, aka Banach spaces, people refer to it as the Banach space adjoint. That is because later on in chapter 4 of this class, we will encounter an operator on Hilbert spaces called the adjoint. And as it turns out, that dual here, or what some people call Banach space adjoint, has some, properties that look quite similar to the Hilbert space adjoint that we will study later on. But these are fundamentally different objects, so I don't want to use the same name for different objects. That's why I prefer dual here. What is also floating around is the transpose. That sort of motivates that notation there, that T. Sometimes people study it in linear algebra. If you have dual spaces in linear algebra, there's the transpose operator, which in the matrix representation just corresponds to taking the transpose of the matrix. So you swap rows and columns. That's why, people call it also transpose operator. But not us. We will stick to dual operator. All right. So of course there's some, possible confusion now, because there's a dual space and a dual linear transformation or dual linear operators. You have to be careful what you're talking about. All right. So anyways, now let's prove this. So many things have to be checked. Let's give this equation up here a star, because we will refer to it all the time. So first let's look if star actually makes sense. So if A is the bounded linear transformation and F is a linear functional, remember these are bounded linear transformations from the space Y into the underlying scalar field. We have that the composition F circle A, so A goes from X to Y, and then F takes Y and maps it to the field. So the whole thing, and it's a composition of bounded linear transformation. So this is continuous. It's a composition of continuous functions. So this is a map from X to the scalar field. So this is a linear functional on X, right? That's what we have. All right. So as composition of linear maps, and of course we can also write as composition of continuous functions. That's why they're bounded, because of our very first theorem in this class. Or you can just use the submultiplicativity of the operator norms and just write down a crude upper bound for that composition, which is this. And this is of course finite, because F is a linear functional, so it's bounded, and A is a bounded linear transformation, so it's bounded. All right, so you have this. So this shows that star indeed defines a bounded linear transformation AT, the dual from Y star to X star. All right, next. Let's compute the operator norm. So a of t. Okay, so now careful. How does this work out? So I have to take a supremum, and now a of t is a map that acts on linear functionals in y, and it spits out a linear functional in f, right? So when I write this down here in the definition, then this norm here is the operator norm on the dual space of x, right? And I optimize over all linear functionals on y that, say, lie on the boundary of the unit ball in that dual space, okay? So this is definition of operator norm, but you have to be very careful. What are the operators acting on and what kind of norms are you working with? All right, so now you have this. So now let's leave the outer supremum as is. And now let's use a bracket. What goes on here inside? So that I just said, this is the operator norm of a linear functional on x, right? So this is the supremum of x over the unit ball, and then A transpose f of x, right? That's what it is, right? So again, in this step, I just look at this guy here, and I remember this is an operator norm of a linear functional on x, and as such, it is equal to this thing here, right? Okay, good. So this it requires some practice. All right, and now inside I use, well, the definition of that ATFX. So supremum f supremum x, and then what do I got there? So the definition was fax. Okay, and now while you start using the submultiplicativity of the norms. So this guy in here is at most f operator norm and then ax in y space, right? And then you can do this is less than or equal, so you keep the operator norm of f as is, and then this is the operator norm of the linear transformation A times the norm of x in x space. Okay, so and then you see outside here you optimize over f and x, so these you set equal to 1, and then what remains is just as an upper bound the operator norm of the bounded linear transformation A, which is finite, right? So you immediately have this inequality, that the operator norm of the dual is at most the operator norm of A. Okay, very nice. Now, also we will now conclude that the converse inequality is true, and for that we use again Hahn-Banach. On the other hand, given x in x, there exists linear functional on y star with operator norm equal to 1, and g(a) of x is equal to the norm of a of x in y space. This was the very first corollary to the Hahn-Banach theorem. The first one was frankly the rephrasing of, I think I call it the zeroth corollary. It was paraphrasing the Hahn-Banach theorems just for the norm, but then the first result after that was precisely this, right? So given any point in a space, you can find linear functional. It was called x naught, the point that f of x naught is equal to the norm of x naught, and the linear functional has operator norm 1. And I said this tells us that the dual space is really, really big. And that's what I'm using here. Okay, so you have this. Good. Hence, again, by star, we have, so let's start from the left, axy, which is equal to, this is a norm, so it's positive quantity, so I can also put the complex modulus around it. So you have this, then g of ax by the definition, this is where I use the star. Here, this is equal to A transpose g of x Okay, and now you do the same, estimate that you did before. So this is at most A transposed G X, and then this is at most A transposed G X, but remember the linear functional here had norm 1, so this is precisely A transposed XX. So now if you look at this being at most equal to this, and now you optimize over the unit sphere in X space, then indeed you conclude that A is at most in operator norm the dual of A, right? And now you can combine these two guys together up here, and you find out that the operator norms of the dual and the linear transformation you start with are exactly the same. Okay, good. Altogether, A transposed is equal to A. And this shows that the map which assigns to a given bounded linear transformations is dual, its dual is an isometry. That's precisely what it says. Okay, it's an isometry. Okay, so now what remains to show is, I think, two things. It remains to show that this map is linear, and then it remains to show that actually, these dual operators are uniquely determined by the equation yellow star. Okay, so since, let's do the linearity and then the other part in the rest. Linearity is easy, since for 2AB in LXY and scalars alpha beta in F, we have f of alpha A plus beta B acting on X. This is, well, by linearity of F, this is F AX plus beta F BX. Now this is by yellow star alpha A transposed F of X plus beta B transpose, not transpose, now I'm using already transpose, the dual F of X. All right, and this is of course how you define the addition of two bounded linear transformations, namely pointwise. So this is equal to this. All right, and this holds for all F in Y star and for all points in X. All right, so now you just compare this side with this side, and you reduce, hence alpha A plus beta B transposed is the dual of it is equal to alpha dual of A plus beta dual of B. Okay, provided the dual is uniquely defined, and this is what I will prove at the beginning of the next video. See you then.